Once again, a very warm welcome to you students. We have now come to the last part of permutations and combinations. This lecture will cover the distribution of identical things into different groups, the concept of derangement, calculation of exponents of different prime numbers in the factorial of any natural number, and last but not the least, we will solve some very interesting problems on this topic. So, let's get started. Distribution of identical objects into different groups. So far we have discussed the distribution of different objects into different groups. But what if the objects become identical now? How we are going to distribute them into different groups? Let's see it. The number of ways in which n identical things can be distributed into r different groups is: first, n plus r minus 1 cr minus 1 if the groups can have 0 objects, and n minus 1 cr minus 1 if the groups cannot have 0 object. It means that if we have got n identical things and we want to distribute into r different groups, then the number of ways is equal to n plus r minus 1 cr minus 1 if the groups can have 0 objects. That is, any group can have 0 elements. And second, n minus 1 cr minus 1 if groups cannot have 0 objects. It means that every group must have at least one object. It cannot have any group having 0 objects. So let's try to understand this concept through an example. Distribute 6 identical apples to 3 boys such that boys can have any number of apples, and the second condition is every boy must have at least one apple. Here n is equal to 6 and r is equal to 3. So from the formula we can have, if the boys can have any number of apples, then the number of ways of distribution is equal to 6 plus 3 minus 1 c3 minus 1, and that is equal to 8c2, and which is equal to 28. So for the first condition, that is the boys can have any number of apples, we get the number of ways equal to 28. For the second condition, that every boy must have at least one apple, here again n is equal to 6 and r is equal to 3. So from the formula n minus 1 cr minus 1 we get as 5c2, and that is equal to 10. Now let's try to visualize this problem. We have arranged these 6 identical apples in a row and inserted 2 identical black markers. Now this has resulted into the division of these identical apples into 3 groups. If we closely see it, we can find that it is nothing but the arrangement of these 8 objects, that is 6 identical apples and 2 identical black markers, that will result into the distribution of these apples to 3 boys. Thus we are going to arrange them, and it can be done in 8 factorial by 6 factorial into 2 factorial ways, which is nothing but equal to 8c2. Why 8 factorial by 6 factorial into 2 factorial? Because we know that if we have got n objects, and out of these n objects p are identical, q are identical, and r are identical of one kind, then the number of ways of arrangement is equal to n factorial divided by p factorial into q factorial into r factorial. So here we have got 6 identical apples and 2 identical markers out of these 8 objects. So they can be arranged in 8 factorial by 2 factorial into 6 factorial, and that is equal to 8c2 ways, and which is equal to 28. Now let's see the second case. In the second case, every boy must have at least one apple. So what we do is, we distribute 1 apple to all the boys, so that every boy gets at least one apple. Now how many apples we are left with? 3 apples, and they have to be distributed among these 3 boys such that anyone can have any number of apples. So now it becomes similar to the previous case, that is any boy can have any number of apples. Now let's try to again visualize it. We have got 3 apples. Now what we do is, we insert 2 identical markers again. Why we are inserting 2 markers? Because it results into division of these 3 objects into 3 groups. Now the apples and the markers have to be arranged among themselves, and these 3 apples and 2 markers are identical, so they can be done in 5 factorial by 2 factorial into 3 factorial ways, and that is equal to 5c2. So we have seen from the two cases that the number of markers that we have to insert is equal to r minus 1, so that the total number of objects become n plus r minus 1. Let's try and see another approach to solve this problem. Our first condition is boys can have any number of apples. So we are going to see the different cases we can have to solve this problem. Let us say the 3 boys are A, B and C. So the first case could be A getting 1 apple, B getting 1 apple and C getting 4 apples. And the number of arrangements is equal to 3, because A can have 4 apples, B can have 4 apples. So as such we have got 3 arrangements for this case. The case 2 could be A getting 2 apples, B getting 2 apples and C getting again 2 apples. And the number of arrangements in this case would be 1. For the third case, it could be A getting 3 apples, B getting 2 apples and C getting 1 apple. So the number of arrangements here is equal to 3 factorial, and that is equal to 6. Case 4 could be A getting 0 apples, B getting 0 apples and C having all the 6 apples, and the number of arrangements in this case is equal to 3. The fifth case could be A getting 0 apples, B getting 5 apples and C getting 1 apple. So they can be arranged among themselves in 3 factorial ways, that is equal to 6. Now the other case could be A getting 0 apples, B getting 4 apples and C getting 2 apples. So again the arrangement in this case is equal to 3 factorial, and that is 6. And the last case could be A getting 3 apples, B getting 3 apples and C getting 0 apples, and the number of arrangements in this case is equal to 3. So what we see is the total number of arrangements is equal to 3 plus 1 plus 6 plus 3 plus 6 plus 6 plus 3, and that is equal to 28. Thus we see that there are in all 28 cases, and this is equal to the answer which we obtained from the formula. Now the second condition is every boy must have at least 1 apple. So again let's construct different cases, and let us say the boys are again A, B and C. So the case 1 could be A getting 1 apple, B getting 1 apple again and C getting 4 apples. So the number of arrangements is equal to 3. Case 2 could be A getting 2 apples, B getting 2 apples and C getting 2 apples. So the number of arrangements here is equal to 1. And for case number 3, that is A getting 3 apples, B getting 2 apples and C getting 1 apple. The number of arrangements is equal to 6. So the total number of arrangements is equal to 10. We can say we have 10 different cases. So 10 is the number of ways we can actually distribute the 6 identical apples to 3 boys, such that every boy receives at least 1 apple. Thus we see that the answer which we obtained through this method is equal to the answer which we obtained through the formula. Let's try and solve another problem. Find the number of integral solutions of the equation A plus B plus C plus D equal to 21, where A is greater or equal to 2, B is greater or equal to 1, C is greater or equal to 4 and D is greater or equal to 1. So what we have to do in this problem is we have to find the number of integral solutions, that is we have to find the values of A, B, C and D such that the values have to be integral, and the equation is A plus B plus C plus D is equal to 21. Also we have different constraints on the values of A, B, C and D, that is A is greater or equal to 2, B is greater or equal to 1, C is greater or equal to 4 and D is greater or equal to 1. So let's try to solve it. The given equation is A plus B plus C plus D is equal to 21, and the constraint on A is greater or equal to 2. So it means that A minus 2 has to be greater or equal to 0. Let us say that A minus 2 is equal to capital A, or A is equal to capital A plus 2. Similarly, B is greater or equal to 1, or b minus 1 is greater or equal to 0. And let us say that b minus 1 is equal to capital B, or small b is equal to capital B plus 1. Similarly, for C and D we can write as small c is equal to capital C plus 4 and small d is equal to capital D plus 1. So what we do is we substitute the values of a, b, c and d in this equation. We get as a plus 2 plus b plus 1 plus c plus 4 plus d plus 1 is equal to 21, or a plus b plus c plus d is equal to 13. All these are capital. Now a, b, c, d can have any value, even 0. So we know the condition is a plus b plus c plus d is equal to 13. Now what we see is, if we divide 13 into identical ones, that is, we have 13 identical ones, and when we add them they result into the number 13. Now what we do is we divide these 13 ones into 4 parts, so that the first part could be A, the second part could be B, the third part could be C, and the fourth part could be D. So what we have done is we have inserted 3 identical markers here. Now the total number of objects now become equal to 13 ones plus 3 identical markers, that is equal to 16. Now they have to be arranged, and they can be done in 16 factorial divided by 13 factorial into 3 factorial, and that is equal to 560 ways. Thus the total number of solutions is equal to 560, and these are the integral solutions. Once again, we have divided these 13 identical ones into 4 parts by inserting 3 identical markers, and then they have been arranged in 16 factorial divided by 13 factorial into 3 factorial, and that is again equal to 560. So the total number of integral solutions is equal to 560. Let's move on to the next topic and find out the number of ways of selecting R objects out of a group of n things in which p are identical. That is to say, we have a group of n things, and out of those n things p are identical. Now we have to select R objects out of these n things. So here 2 cases are there. Case number 1, if R is less than equal to p, then the number of ways is equal to summation R equal to 0 to R equal to R n minus p CR. That is, if the number of objects we want to select is less than the number of identical objects, then the number of ways of selecting those R objects is equal to summation R equal to 0 to R equal to R n minus p CR. The second case is, if R is greater than p, then number of ways is equal to summation R equal to R minus p to R equal to R n minus p CR. Let's try to solve an example to understand this concept. A cricket team of 11 players has to select 11 bats from a set of 18 bats, out of which 6 are identical. Find the number of ways in which the team can select the 11 bats. That is to say, there is a set of 18 bats, and out of those 18 bats, 11 bats are to be selected, but given that 6 bats are identical, so we have to find the number of ways in which those 11 bats can be selected from a group of 18 bats in which 6 are identical. Now the solution is as follows. Here n is equal to 18, p is equal to 6 and r is equal to 11. So we see that 11 is greater than 6, that is r is greater than p. So the number of ways is equal to summation r equal to 11 minus 6 to r equal to 11, 18 minus 6 CR, and that is equal to 12C5 plus 12C6 plus 12C7 plus 12C8 plus 12C9 plus 12C10 plus 12C11. Now 12C5 plus 12C6 is equal to 13C6. 12C7 plus 12C8 is equal to 13C8, and similarly 12C9 plus 12C10 is equal to 13C10 plus this term 12C1. Now this can be further calculated. You can further solve it and find the exact value. Now let's try to see this problem in a tabular manner and how we have actually solved it. what we see is the total number of objects is equal to 18. Out of those 18 objects, different objects equal to 12 and the identical objects are equal to 6, and we have to choose 11 objects. So let us say in the first case we have chosen all the 6 identical objects. Now we have to choose 11 objects, so that 5 objects have to be chosen from a set of different objects, that is 12 objects. So this selection could be made in 12C5 ways. The selection of 6 identical objects out of 6 identical objects can be done in only one way. So the total number of ways is equal to 12C5 in case 1. For the case 2, again the different objects is 12. Identical objects, let us say we choose 5. So the different objects that we have to choose becomes equal to 6. So the selection would be 12C6. In the third case, we have again 12 different objects. Let us say we choose 4 identical objects, which could be done in one way. Now out of 11 objects, we have chosen 4 identical objects. So 7 different objects have to be chosen, and that has to be chosen from the group of 12 different objects, which can be done in 12C7 ways. Thus the total number of ways equal to 12C7. For the next case, let us say we choose 3 identical objects. Now we need to choose 8 different objects from a set of 12 objects. So the total number of selections become 12C8. In the next case, let us say we choose 2 identical objects. So we have to choose now 9 different objects from a set of 12 different objects, which can be done in 12C9 ways. The next case would be we choose 1 identical object. So again, how many objects we have to choose different is 10, and out of a group of 12 different objects. So this becomes equal to 12C10. And finally, let us say we choose 0 identical objects. Then 11 different objects have to be chosen from a group of 12 different objects. So the number of selections in this case would be 12C11. Thus the total number of selections would be equal to 12C5 plus 12C6 plus 12C7 plus 12C8 plus 12C9 plus 12C10 and plus 12C11, which is the same which we obtained from the formula. Now students, let me ask you something. What exactly is derangement? Now if the thing that strikes your mind is it's a kind of arrangement, then I would say 10 on 10 to you guys, because it is definitely a kind of arrangement. But what exactly it is? It is the permutation or arrangement of the elements of a set such that none of the elements appear in their original place. It means that if we have 4 objects A, B, C, D, and we have 4 groups A, B, C, D, A such that A belongs to group A, B belongs to group B, C belongs to group C, and D belongs to group D. Now we have to arrange these objects in these 4 different groups such that A does not appear in A, B does not appear in B, C does not appear in C, and D does not appear in D. Then this type of arrangement or permutation is called as derangement. That is, the elements do not appear in their original place. None of the elements appear in their original place. Now derangement is equal to n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on up to minus 1 to the power n into 1 by n factorial. Now let us try to see an example to understand what derangement exactly is. This is a solved example that appeared in IIT JEE 1992 and states that there are 4 balls of different colors and 4 boxes of colors same as those of the balls. The number of ways in which the balls in each box could be placed such that the ball does not go to the box of its own color. It means that we have got 4 balls of 4 different colors and we have got 4 boxes and their color is the same as those of the balls. Now we have to place these balls in each of the boxes such that none of the ball appear in the box of its own color. Now this is a typical and a particular case of derangement. Here let us say these are the 4 boxes and correspondingly these are the 4 balls. That is, this ball and this box have the same color, this box and this ball have the same color, and similarly for these two boxes and these two balls. So here n is equal to 4. Thus the total number of derangements, or the total number of ways in which no ball goes into the box of its own color, are equal to 4 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial, and that is equal to 4 factorial into 1 by 2 minus 1 by 6 minus 1 by 24, and that is equal to 9. Thus the total number of ways in which no ball goes into the box of its own color is equal to 9. Let's look at another approach to solve this problem. Let us say we have got 2 balls and 2 boxes. Now the number of ways to place those 2 balls in 2 boxes such that all of them go into the wrong box. We have number of such ways is equal to total number of ways minus the case in which one ball is in the right box and minus the case in which all are in right box. So what we see is total number of ways is equal to 2 factorial, as we have 2 balls and they can be arranged among themselves in 2 factorial ways. Now the case in which all are in right box will be equal to 1, because we have only one condition and one case where we can place all the right balls in the right boxes. Now the case 1 is in right box. If I say that I have placed one ball in the right box, then the second ball will automatically be placed in the right box. So these two cases, all are in right box and one is in right box, are actually the same. So we count them as 1. Thus the total number of ways is equal to 2 factorial minus 1 minus 0, and that is equal to 2 minus 1, or equal to 1. Thus the number of ways to place 2 balls in 2 boxes so that all go into the wrong box is equal to 1. Now let's try to find out the number of ways in which we can place 3 balls in 3 boxes so that all of them go into the wrong box. Now this is equal to the total number of ways minus all the balls are in the right boxes minus 1 is in right box and minus 2 balls are in right box. Now the total number of ways is equal to 3 factorial, because there are 3 balls and they could be arranged among themselves in 3 factorial ways. Minus 1 because all are in right box, and there's just only one way of arranging or placing all the balls in the right boxes. Now the case where 1 is in right box, that is 1 ball is in the right box and 2 balls are in the wrong boxes. So we first choose 1 ball which is in the right box. This could be done in 3C1 ways, and we have seen that arrangement of 2 balls in 2 boxes where all of them go into the wrong one is equal to 1 here. So we multiply it with 1 minus the case 2 balls are in right box. This is the same as all are in right box. So when we solve this, we get the total number of ways to place 3 balls in 3 boxes so that all of them go in wrong box is equal to 2. Now let us say we have 4 balls and 4 boxes, and we have to arrange them in such a manner so that none of them goes into the right box. Now this is equal to the total number of ways minus all are correct, minus 1 is correct, minus 2 are correct, and minus 3 are correct. Correct means the right ball is placed in the right box. Now the total number of ways is equal to 4 factorial, as we have got 4 balls and they have to be arranged among themselves. So that can be done in 4 factorial ways. Minus 1 because all are correct, and that could happen in only one case. Minus 1 is correct. So what we do is we choose 1 ball which is correct, and the remaining 3 balls have to be placed in 3 wrong boxes, which we have seen is equal to 2. Minus 4C2 into 1. 4C2 because we again select 2 balls that are to be placed in the correct boxes, and that could be done in 4C2 ways. Multiplied by 1 because now we have to arrange 2 balls in 2 boxes so that none of them goes into the right place, and that could be done in only one way, which we have seen before. So minus 0 because 3 are correct, and that is, this case is similar to this when all are correct. So it becomes equal to 24 minus 1 minus 4 into 2 minus 6 minus 0, and that is equal to 9. Thus what we see is the derangements can take place in 9 ways where none of the ball goes into the right box. In this approach, what we have done is, first we have tried to find the number of ways in which we can place two balls in two boxes so that none of them goes into the right box, and that is equal to 1. In the second case, we have seen the number of ways to place three balls in three boxes so that none of it goes into the right box, and that is equal to 2. Another case, we have tried to find the number of ways to place four balls in four boxes so that none of it goes into the right box, and that is equal to 9. Thus, derangement can take place in 9 ways in this case where there were 4 balls and 4 boxes. Now students, let us look at a way to know the exponent of a prime number in n factorial. Here n is any natural number. The exponent of a prime number p in n factorial is given by ep n factorial equal to bracket n by p plus bracket n by p square plus bracket n by p cube plus up to bracket n by p to the power k, where k is the largest number such that p of k is less than equal to n is less than p to the power k plus 1. Here the quantity under bracket n by p is the greatest integer, that is, this bracket represents the greatest integer. So what we can say is, any exponent of a prime number p in n factorial is given by this formula, where k is the largest number such that p to the power k is less than equal to n, which is less than p to the power k plus 1. Here the bracket sign represents the greatest integer. Let's look at an example to understand this formula. How many zeros are there at the end of 78 factorial? So we have to find the number of zeros at the end of 78 factorial. 78 factorial is equal to 78 into 77 into 76 up to 1. So we have to ultimately find the number of zeros in this product. So let's look at the solution. We know that a 0 is formed by the product of 2 and 5. That is, a 10 is formed by the product of 2 and 5. So what we do here is, we try to find the exponents of 5 in 78 factorial and the exponents of 2 in 78 factorials. So first of all, the exponent of 2 in 78 factorial is equal to greatest integer of 78 by 2 plus 78 by 4 plus 78 by 8 plus 78 by 16 plus 78 by 64, and that is equal to 39 plus 19 plus 9 plus 4 plus 1, and that is equal to 72. Here we haven't extended the power of 2 till 7, that is 128, because the greatest integer function of 78 by 128 will be equal to 0. Thus we stop at 64. So the exponent of 2 in 78 factorial is equal to 72. Now we try to find the exponent of 5 in 78 factorial. That is equal to 78 by 5 plus 78 by 25. That will be equal to 15 plus 3, and that is equal to 18. Again we do not extend the power up to 3 because 125 is larger than 78. So the exponent of 5 in 78 factorial is equal to 18. So what we can say is, we can write 78 factorial equal to 2 to the power 72 into 5 to the power 18, and so on. It could be expressed as a multiple of different prime numbers. Now here we know that a 0 is formed when a 2 and a 5 are combined together. So what we see here is, we have got 18 5s and 72 2s. So the number of 5s here determine the number of zeros as they are less in number than the number of 2s, because number of 5s are 18 and number of 2s is 72. Thus we see that when we combine 1 5 and 1 2, then it results into a 0. So here the number of 5s are actually the determining factor for determining the number of zeros. Thus we can say that the total number of zeros in 78 factorial is equal to the power of or the exponent of 5, that is 18. Once again, what we have done here is, we have found the exponent of 2 in 78 factorial and found the exponent of 5 in 78 factorial. The exponent of 5 in 78 factorial is 18 and the exponent of 2 in 78 factorial is 72. As we see the number of 5s, that is the exponent of 5 is less than the exponent of 2, that is 18 is less than 72. So what we say is, the total number of zeros in 78 factorial is equal to 18. So students, that was all the theory on permutations and combinations. I hope you have understood all the concepts with much of clarity. Now let us look at some very interesting problems on permutations and combinations as they find wide applications in calculations. So let's start. The first solved example is: find the number of ways that are possible on this 6x5 grid to go from A to B in the shortest way. That is to say, we have a 6x5 grid, that is 6 rows and 5 columns. So in all we have got 30 such blocks here. We need to find the number of ways that are possible on this grid to go from A to B, this point to this point, but in the shortest possible way. So how to do it? How we got to proceed in this question? So let's see the solution of it. If we closely look at the grid, we see that in order to reach position B from A, one has to take 6 steps left, that is towards the east direction, and 5 steps up, that is towards the north direction. So what we can say is, in all one has to take 11 steps to reach from A to B in the shortest possible way. Now from these 11 steps, we need to choose 6 steps for the left, and that can be done in 11 C6 ways. Now how many steps we are left with? 5. So the rest of the 5 steps can be chosen in 5 C5 ways. So the total number of ways equal to 11 C6 into 5 C5, and that is equal to 11 C6, as 5 C5 is equal to 1. So 11 C6 ways is equal to 693. Again we see that to reach position B, one has to take 6 steps towards the east and 5 steps towards the north. Now in all there are 11 steps. From these 11 steps, one has to choose 6 steps for the left, and that can be done in 11 6 ways. The rest of the 5 steps, that is for the north, can be chosen in 5 C5 ways, and that is equal to 1. So the total number of ways become 11 C6, and that is equal to 693. Let's solve another problem. Find the number of triangles that can be formed by using all the vertices of the octagon. Also find the number of diagonals of an octagon. Here what we have to do is, we have to construct as many triangles as we can by using all the vertices of an octagon, and we have to find the number. And in the second part, we have to find the number of diagonals of an octagon. So how to do it? How to proceed? Let's look at an octagon. Here what we have done is, we have taken 2 vertices. Let us say they are A and B, and we choose another vertex, that is C. Now we construct a triangle by joining A, B and C. So here we see that an octagon has 8 vertices, and any triangle like ABC can be formed by joining any 3 vertices. So the total number of triangles that can be formed by using all the vertices of an octagon is equal to 8C3, and that is equal to 8 factorial divided by 5 factorial into 3 factorial, and that is equal to 56. Now let's look at the second part of it. Here we have to find the number of diagonals. Now what we see is, a diagonal can be formed by joining any 2 vertices, but we also see that the sides of a polygon are also formed by using 2 vertices. That is to say, this side, this side, this side, this side and so on are formed by using 2 vertices of any polygon. So what we see is, the number of diagonals can be written as equal to 8C2 minus 8. Now 8C2 represents the number of line segments that can be formed using 2 vertices of an octagon, and 8 represents the number of sides of an octagon. So what we can say that the number of diagonals is equal to 8C2 minus 8, and which is equal to 28 minus 8 equal to 20. Thus we see that the number of diagonals of an octagon is equal to 20. Now let us look at one more example. This example helps us to find the number of squares and number of rectangles. So it follows as, find the total number of squares in a 8x8 chessboard. Also calculate the total number of rectangles in the same chessboard. So what we have been given is, we have a chessboard 8x8, and we have to find first the total number of squares in this 8x8 chessboard, and second, find the total number of rectangles in the same chessboard. So the solution of it is, Let's look at the first part, that is calculation of number of squares. So this is a 8 cross 8 square board. Now first we have to calculate the total number of squares. So what we see is here that first we calculate 1 into 1 squares. So this is a 1 cross 1 square, 1 cross 1 square, 1 cross 1 square, that is 1 unit multiplied by 1 unit. So for the first row we see that there are actually 8 number of squares, and similarly if we go column wise we see that there are 8 such 1 cross 1 squares. So in all there are 8 cross 8, that is equal to 64 such squares. For a 2 cross 2 square we see that this can be a square, next this can be a square, next this can be a square, next this can be a square, and so on up to here. So there are in all 7 options. And when we go down column wise we see that this is a square, then this is a 2 cross 2 square, then this is again a 2 cross 2 square, and so on till we have got 7 options. So in all we see that there are 7 cross 7 options. So for a 3 cross 3 square we see that this is a square, then again this is a square, this is a square, this is a 3 cross 3 square, and so on, and we find there are actually 6 options. When we go column wise, then again this is a square, 3 cross 3 square, this is a 3 cross 3 square, this is a 3 cross 3 square, and so on. So we see there are 6 options. So in all there are 6 cross 6 options. Similarly for a 4 cross 4 square we have 5 cross 5 options, and for 5 cross 5 we have 4 cross 4, 6 cross 6 squares we have 3 cross 3 squares, and for 7 cross 7 squares we have 2 cross 2 options. And for 8 cross 8 square we have 1 cross 1 option. Thus we see that the total number of squares is equal to 8 square plus 7 square plus 6 square up to 2 square plus 1 square, and that is equal to 204. Once again, for the calculation of number of squares we first calculated the number of 1 cross 1 squares, and that is equal to 64. The number of 2 cross 2 squares is equal to 7 square, that is equal to 49. The number of 3 cross 3 squares is equal to 6 square, and so on. So finally the total number of squares is equal to 8 square plus 7 square plus 6 square plus up to 2 square plus 1 square, and that is equal to 204. Now in the second part we are going to find the number of rectangles. What we see is that any rectangle is formed by 2 vertical lines and 2 horizontal lines. Thus what we see is here we have got 9 vertical lines and 9 horizontal lines. We can clearly see that this is one line, this is one line, this is one line, this is one line, and this is one line, this is one line, this is one line, this is one line, and this is one line. So in all there are 9 vertical lines. Similarly we have got 9 horizontal lines. So what we do is we choose 2 horizontal lines from 9 horizontal lines in 9 C2 ways, and we choose 2 vertical lines from 9 vertical lines in 9 C2 ways. Thus what we see is the total number of rectangles in a 8 cross 8 square chessboard is equal to 9C2 into 9C2, and that is equal to 36 square, which is equal to 1296. Thus the number of rectangles in a 8 cross 8 chessboard is equal to 1296. Oh, we come to the end of a very interesting chapter in mathematics, that is permutations and combinations. But I really hope that you enjoyed learning the concepts taught in this lecture and the previous 2 lectures. Please practice as many problems as you can find on this chapter, as this forms the very basis of many other chapters. So till then, all the best for your preparation and take care of yourself. For more doubts and queries, visit our site www.topIITcoaching.com. We are committed towards perfecting IIT preparation. Thank you.